This video is about interpreting data from a graph, and it's really about MYP criteria C2. So this is the part where after you've processed your data and presented that data, usually in a graph, you now have to interpret that data and you have to try to answer your research question. So I've broken down the interpretation or the strand C2 into essentially 4 bits. They kind of all overlap, but there are different things that you should be doing here. You want to be looking at the data and describing the trends. You want to be commenting on accuracy and precision, and then trying to fully answer the research question, or answer the research question to the extent that you can, given your data. Okay, so what could we say if we were trying to describe the trend? Let's focus on the experimental values, which are the ones in blue, the ones with the error bars. So the simplest description is that as the number of carbon atoms increases, so I'm just going to shorthand here, as the number of carbon atoms is increasing, I can see that the specific energy values are going down. So that's a valid statement, but it is a little bit vague. We can try to get more specific. The next level we could say is that, well, according to our data, we have fit a linear trend line to that. So it looks as though there is potentially a negative linear relationship. So there's a line that seems to pretty closely fit our data, and it has a negative slope. So it's going down as the number of carbon atoms goes up. So saying that something has a negative linear relationship is more specific than just saying as one goes up, the other one goes down. Now I can comment on things about that trend line. So I could say the trend line that we've added has a slope that is minus 5.44, and I should always include units when I talk about a slope. So the units of slope are always going to be whatever is on the rise or the y-axis over the run. So the rise has a units of kilojoules per gram, and then the x-axis has the unit of the number of carbon atoms. So this is per added carbon atom. So let's try to interpret what this slope means. It's basically telling us that for every additional carbon atom in an alkane, which is what this processing was based on. So for every carbon atom, the specific energy of that alkane seems to go down on average by 5.44 kilojoules per gram. So now we're getting really specific. Based on our data, we can actually suggest a quantitative relationship that for every additional carbon atom on an alkane, you will lose around 5.44 kilojoules per gram of specific energy value for that alkane. Excellent. And then the last thing is, if we are going to be talking about this line, we need to comment on if it's a good fit or not. So the R squared value is telling you how good a fit is this trend line for your data points. And you can kind of tell just by looking at it that, you know, it's not perfect. None of the data points are actually on that line, but it's pretty close to most of them, and it is within all these error bars, which we'll talk about soon, of the data points. And if you're looking at the actual R squared value, if you had an R squared value of 1, that would imply that every data point was on that line. And so it would be essentially a perfect fit. So obviously we don't have a value of 1, we have an R squared value of 0.926. So that's not fantastic. You know, something like 0.99, 0.98 would be better, but this is still above 0.9. And so I'd say that if R squared is greater than 0.9, then you can comment that this trend line that we've been interpreting, a negative linear relationship, and that we are going to decrease 5.44 kilojoules per gram per carbon atom, this is a pretty good fit for the data. So if we had a very low value and if it was clearly a very bad fit for our data, then interpreting and stating that our data shows a negative linear relationship and trying to interpret the slope really specifically wouldn't have a lot of meaning if the trend line was a bad fit for the data. But since the trend line is a reasonably good fit for the data, we can interpret the type of relationship and we can interpret the slope, and that probably has some value in our conclusion. Okay, so we've described the trends and we've tried to do it very specifically. We've tried to talk about the type of relationship and the meaning of the slope, including units, and we've talked about how good the trend line fits the data. Now, let's talk about how accurate and precise this data is. These are two terms that really get mixed up a lot, so let's clarify them. Accuracy is a measure of how close something is to the true value. So in here, the true values are these values up here. These are the literature values. So we can see that essentially the distance between the orange dots and the blue dots, that represents our inaccuracy, how far off we are from the true values. Now, in your lab report, you will have also calculated percent error, which is the same thing essentially. How far off are you? But as a visual, you can look at your graph and you can see the distance between them, just to give yourself something to discuss. It's kind of helpful to see how inaccurate you are. Okay, if I was going to talk about this, I would say that in terms of accuracy, sorry, in terms of accuracy, at least in both the literature values and the experimental values, we have this negative linear trend. So that seems to be, even if it's not perfectly linear, this negative trend that is close to a linear relationship, that seems to be present in both our experimental data and the literature values. And so that's something I can point to about my data that seems to be pretty accurate. As the number of carbon atoms is increasing, the specific energy is decreasing in a mostly linear fashion. So there is some aspect to our data that seems to be accurate. At the same time, we can see that our specific energy values are, there are many ways that they are inaccurate. And so the ways that they're inaccurate is our values seem to be significantly lower than the literature values. I can also see that our trend line is a lot steeper. If I compare the slopes, the slope in ours was minus 5.44, where the slope in the literature values is only minus 1.66. So for our data, the way that the specific energies were decreasing was much faster than it actually does for the literature values. So we have a faster decrease. So minus 5.44 versus minus 1.61 kilojoules per gram per carbon atom. And so, maybe we could try to interpret why that might be. It seems that as our carbon atoms are increasing, we're getting farther and farther away from the true value. So maybe that has to do with how well those longer chain alkanes burn. How completely do they combust? Maybe there's a greater level of incomplete combustion as we get longer. And that's why we're getting farther and farther from the true value in our experimental values. That would be quite an advanced thing to try to think through and push to. But we've got the literature values to compare to for accuracy, and so we can point out maybe some aspects of our data that are accurate and some aspects of our data that are inaccurate when we compare to the literature values. Okay, now since I want to focus on precision, I'm going to get rid of, sorry, my eraser keeps going away. There we go. I'm going to talk about precision. Precision has to do with how close together a series of measurements are for the same value. And in other words, I think a good way to describe precision is certainty. If you're able to repeat an experiment or repeat a bunch of measurements and they're all very close together, like they should be, then that means you're very certain about those measurements or about those calculated values. But if you repeat something and your values are pretty widespread, they're quite varied and they're all over the place, then you are not very certain, and so you have a lot of uncertainty, and that would be imprecise. So if we look at our data, the thing that represents precision for us are these error bars. And so we could talk about how in our data, the one for methane, the one carbon alkane that's right here, this has the smallest error bars. So this is our most certain, most precise value. The multiple trials that we did burning methane, the values that we got for specific energy were within quite a narrow range. So that means that we're more confident about the value of the specific energy of methane than we are for the other fuels. We can see that all the other ones have fairly large error bars. So these are less precise. We have less certainty, or we could say more uncertainty about these values. So I would say we don't know these other four values with a whole lot of certainty because of those giant error bars. And if you see, a lot of the error bars actually overlap one another. So if I look at these middle three, right, the values that we were getting for ethane compared to propane compared to butane, right, you can see that there's a huge level of overlap between the ranges. If I'm kind of highlighting that now. Even the pentane would sort of overlap down here with the butane, but it's sort of on its own. So we'll get rid of that one. But looking at the error bars of neighboring data points and thinking about whether or not they overlap, based on our data, I would say that ethane, propane, and butane basically had the same specific energy values. There was hardly a significant change, or I can't be certain that there was a big significant change. So when you've got overlap between error bars, there's not much, if any, significant difference. So we can clearly tell from our data that methane seems to stand alone as being the alkane with the highest specific energy. And we know that with a good deal of certainty because of the small error bars. We can see that the pentane pretty clearly has the lowest. It's also relatively precise compared to the others. We know it's the lowest because its value also doesn't really overlap with any of the others, and its error bars hardly overlap at all with any of the others. But with these middle three, in terms of our own data, their specific energy values seem to be largely the same. There's not much of a difference between them. We have very little precision about these values, so we know these values with very little certainty. And because their error bar ranges, their uncertainty ranges overlap, we could basically say that there's not much difference between the specific energies of ethane, propane, and butane. Okay, and then finally, we've done all three of those, so answering the research question. So in this lab, the research question would be, how does the number of carbon atoms in an alkane, in a straight chain alkane, affect its specific energy? And so we could say some things with confidence. We could say that as the number of carbon atoms is increasing, we know that the relationship is that the specific energy of the alkane is decreasing. And we can be fairly confident in that trend because that trend matches that of the literature values. It's the same type of trend. And that trend is it is some kind of a negative linear relationship, is a pretty good fit to describe that trend. So the specific energy goes down in sort of a constant way as you add a carbon atom. However, beyond that, because of our large uncertainty, as well as our very large inaccuracy and percent error, we can't really state anything else with much confidence or significance because of the large amount of inaccuracy and the large amount of imprecision in our data. So we could say some things, we can somewhat answer the research question with confidence, and then there are things that we can say we can't answer the rest or give any more specific type of answer because of the limitations of our data.